Okay. All right. Uh, so the unit we're starting here is thermal physics, and it deals with the concept of, I guess, heat dynamics, or the movement of heat, what heat is, and how everything works, I guess, at the kind of atomic level in terms of what heat and temperature and internal energy and so on are. So I suppose one of the first things we should do is we should define, I guess, what we essentially, how we think about matter first of all, and then how heat applies to that. Okay? So let's start there. Let's just discuss matter in general. Uh, so in modern times, we use particle theory to describe the way that the physical world is made up. All right? So all matter is composed of some type of small particles. Okay, these are either atoms, or they may be molecules. Can you think of any other possibilities that might make up matter besides atoms, or, groups of atoms called molecules? Is there anything else? I guess ions too, sort of a special case in terms of in ionic compounds. That's kind of what you're looking at. So atoms, molecules, or ions. And matter tends to exist in one of three states. Well, let's talk about normal states of matter, okay? Solid, liquid, gas. There are some exotic states of matter that happen at, say, for instance, very high temperatures, such as plasmas, which would be basically what, I guess, the sun is mostly made of, or even to a certain extent, fire. But we are used to dealing with matter in its three common states. So let's just see how that's going to kind of work in terms of where the particles are and what the particles are doing in those states. So if we imagine a block of solid material, we were to zoom way in to its, tiniest level of structure, what you're going to find is you're going to find an organization of small particles, and let's say this is a hunk of metal, for instance, all right? You're going to have kind of a regular sort of a pattern of these particles inside the metal, and I'm trying to make it look 3D. It's a little tough to do. Okay, so this is meant to be like a cube of metal going back into the page. Okay, so these particles are associated with each other. As you know, I'm sure from chemistry class, there's some sort of attraction or bonding between them. Whether it's a true, fully chemical bond or it's something like van der Waals forces and so on, depends on the type of material it is. But we can kind of generalize with a solid and say that these particles are attracted together, and that they are associated to one another. And a good way of thinking about them is as if they're all attached together by little springs. Okay. In reality, these springs are forces. Okay. And electromagnetic forces is probably the best way to describe them. Okay. And what that means is, although they're attached together, like as if they were attached with springs, there is some room for them to move, okay, within this sort of framework, all right? And so they do. They tend to oscillate, if you will, around sort of fixed points, and they kind of jiggle. They sit there and jiggle, okay? So this is kind of of how we're going to think about solids, okay? Liquids are similar but a little bit different. With liquids, okay, there is an association between the particles, but the regularity that they would have had with solids is gone. So these particles are now much more, free to move around. They've sort of broken whatever type of bond was holding them together, that they have not completely dissociated with each other. So they're still attractive forces, but it's as if the springs have become very, very loose or actually become non-existent, and now these can associate with multiple different particles. And what that does is it gives the liquid the property that it can, pour, for instance, right? So we can pour a liquid because all of these particles can oscillate around each other and flow past one another. I like to think of it like a big jar of beans or peas or something. You can pour the jar of peas even though it is made of little solid particles. Okay, and then the last scenario is gases. Now with gases, especially with what we'll talk about later, theoretical ideal gases, the particles are disassociated completely from one another and now can move freely throughout space. Okay, and we define these kind of differently in terms of the way we describe them. So for a solid, it has a fixed volume, and a fixed shape. Liquids are different, they still have a fixed volume, but their shape is changeable. So no fixed shape. And gases, I'm sure you can guess, have no fixed volume and no fixed shape. Okay, so now we look at these three states, and there's a good example that's around us at all times, and that's water. Okay, this would represent water as ice, water as its liquid form, and water as steam or vapor. Okay, so the question is, how do I get from one to the next, to the next, to the next, and how does that apply, or how does the concept of heat apply to all of this? I think this is probably nothing really all that new to you guys, but I guess, well, first, before we even get into how you get from one state to the next in terms of, say, water as an example, we should probably define heat to begin with. Okay, so just let me pause for. Okay, so so heat. What is heat? Heat is what is heat? Heat is it's hard to, I don't know, I have a tough time defining this, but I'm going to try my best. Heat is the energy responsible for increasing the kinetic energy of particles of matter. Okay. So heat on its own is a really hard concept to think about because it's sort of like nothing, really, in a way. So what I mean by that, like, so I want to put heat into here, right? Like, let's say I have this lump of ice or an ice cube, and I want to melt it. Well, we know you got to put heat in, but what is heat? Like, how are we getting heat to begin with? You see what I'm saying? So, like, to get heat into the ice cube, we have to, like, heat up the area around the ice cube. So let's say the area here around the ice cube is made of air, all right? And let's just look at and say, well, air is made up of a mixture of different particles. Let's just represent air particles as purple circles, okay? So here's purple circles, okay? Now, if I want to heat up the ice cube, some have to increase its kinetic energy, right? So one way to do that is to heat the air around the ice cube and then allow the energy to transfer into the ice cube, okay? So the way I'm thinking of, right, is these particles of air with an elevated velocity have to come in here and collide with particles of the ice cube, and via, momentum concepts, essentially, transfer some of their velocity, or some of their momentum, I should say, into these ice cube particles thereby causing it to vibrate at a more elevated rate, right? But in doing that, I then remove some of the momentum and therefore some of the kinetic energy from the air particle itself. Okay? It's all about motion, right? So we're actually trying to think of the physical process that must be going on when we're heating this thing. Now that's not the only way to transfer heat into here. This is heating via, if you want, conduction. Okay, so you actually have to have a collision between the two types of particles, one with high, if you want, EK to begin with, and then have to transfer some kinetic energy directly through contact into this slow-moving or low EK particle here. That's one way to get heat in. Okay, what's another way that you know of to get heat in there? Okay, well, convection, okay, convection is interesting. So what's convection if we say convection? What does that mean? Yeah, convection is interesting in that it's a way to transfer heat, but it's actually a motion of a volume of either liquid or gas. You know, the best idea to think about that is, say if I had a pot of boiling water on the stove, it gets hot in one area, okay, the energy transfers into those particles over here, they start to move around, and the space between them gets larger, they become less dense, and they rise within the volume of liquid that's cooler, and new liquid comes in to replace them, and that moves heat around. Convection is more of a way of moving heat around in an area, versus this, which is actually a direct transfer of heat from one area to another, okay? So if I jiggle this guy, right, well then that jiggle of energy gets transferred through to whatever is nearby and attached to it, right? And the heat, if you want, spreads through the cube kind of slowly. And you know that ice cubes kind of melt from the outside in. They don't just sort of melt that way. And this is essentially the main process that's going on here. Could I melt an ice cube if it were in a vacuum, though? Is there a way to do that? Okay. Okay, radiation. Good. So someone said microwave radiation. Yeah. There is one other way to get heat in here, or get energy in here, and that is through radiation. Okay, so what's radiation? Well, radiation is electromagnetic waves which travel through space that happen to be at the right frequency to help oscillate or move the ice particles around. Because all electromagnetic energy heat up matter. Maybe. It might. Some frequencies are much better at it than others, but it is a transfer of energy, right? Right. 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 So I mean, for us, it just so happens that infrared is what heats matter really well. Microwaves also do it specifically for water. UV is a transfer of energy, but it doesn't tend to make heat, but it does tend to disrupt the bonds between atoms, right? So if you get smaller or smaller wavelength or higher frequency energy, it doesn't make heat in the same way that like infrared or microwaves do, but it does transfer energy from one place to another, and it just so happens that that energy will attack the bonds between the molecules inside your body because it's got a shorter wavelength and so on. Longer wavelengths like radio waves and so on, you also don't tend to feel hot. We're all bathed in radio waves all the time and we don't necessarily feel warm from them, but they're also transfer heat, but you're talking wavelengths now in the order of 1 meter to 1 kilometer and so on. So their interaction with matter is going to be different. But since you mentioned microwaves, microwaves do stuff to water molecules. I'm not going to get into what they do. Well, they flip them around essentially, and they interact with some of the bonding between here. But radiation can bring heat in here. The radiation itself, right? This stuff, like whatever this is made of, do you know what this is made of? Do you know what the electromagnetic waves are made of? No, me neither. No, I don't know what they are. They're waves and particles and photons and energy, but on their own, I don't know what they are. We know them because of their interactions with stuff we can sense, but what are they on their own? I don't know. Yeah, it's one of those things, right? Like if a tree fell in the forest and no one was there to hear it, does it make a sound? Like these exist because of how we see their results, but can you actually like interact with them directly without interacting with them with like test instruments? And there you get the whole like, can you interact with something without changing it? You know. Anyways, so what's the true nature of radiation energy? Well, it's electromagnetic waves, but what that really means, I'm not sure. What it can do is it can be absorbed into the atoms or the electrons around the atoms and into the bonds and so on, and that can cause flipping or vibrating or whatever, and that is essentially going to be able to increase the temperature of objects. Okay. Sorry if I didn't do a good job of explaining that. I find it a very difficult subject to explain accurately. You can just say like heat's the kinetic energy, but then like what does that mean? Is heat actually the kinetic energy, or is that like what we sense as? Or is that what allows us to sense heat? You know what I'm saying? I don't know if you know what I'm saying. Okay, so let's talk a little bit about this concept of internal energy as well. Okay, internal energy. So the internal energy of, say, like a block of matter here is the sum of all kinetic energy of all particles within it plus any potential energy that it contains. So when you hear internal energy, it's a little bit different than the heat energy, okay? Heat energy is the vibrations or the kinetic energies only of the molecules, right? That vibrate and move and so on. The internal energy includes things like the energy like located within the chemical bonds between the atoms and the molecules. You might even extend it to the limit where you're now talking about the actual energy in the mass itself, like equals mc squared. So you have to be a little careful with internal energy versus heat, right? Because if I take say I take a cube of iron, right, for instance, and now we're going to get into the concept of temperature here, but let's say I take a cube of iron, okay? So just imagine a block of iron, a little block of iron, okay? And let's say right now this block of iron is at 20 degrees Celsius, or just around room temperature, say, depending whether you like your rooms at 20 or 25. I prefer 20, but say 25. The particles within there, okay, like first of all, iron's going to be solid, right? It's solid. I don't know what its melting temperature is, but I assume it's pretty high. 1700 degrees Celsius, something like that. Yeah. Fahrenheit. What? What's Fahrenheit? Let's not even talk about Fahrenheit. Okay, so we've got the particles in here, they're jiggling around, right? So we can say, right, that the total internal energy here is the energy in the attractive bonds between the iron itself, okay? It takes energy to put in to break those, to say melt iron and then turn iron into a gas. You have to put energy in to do that. So there's that. Okay, so there's some energy within the bonds themselves. There's the energy in the mass of the iron, and then there's kinetic energy in the jiggling of the iron atoms. Now let's say we start to cool it down. We go to 0 degrees Celsius, we go to minus 100 degrees Celsius. Eventually we get down to a magic temperature. You know what that is? About negative 273 degrees Celsius. At that point, what happens to the atoms within the iron? Right. Well, they might actually, yeah. Well, we know theoretically, we have to be careful with how we describe this, okay? We know that below this temperature, at this temperature, the concept of temperature doesn't make sense anymore. At this temperature, no atoms are moving anymore, okay? So their kinetic energy is stopped. So as we cool, the vibrations within here get less and less and less and less and less, lower and lower, and then at that temperature, the kinetic energy is gone from the iron atoms. They're just sitting still now, okay? Completely still. The electrons are still there. Are the electrons still moving? Well, it depends. It depends how you think about an electron. If you think of it as an actual mass-containing particle, then I think, yeah, it probably would be stopped at that point. But if you think of it as a smear of charge or potential, okay, well then there's still something holding these together, right? And it's got to be the relationship between the atoms, the nuclei of the atoms, and if this is a metal, the paste of negative electric charge that sort of floats around outside. Can you make electricity transfer through something? Yes, you can. In fact, interestingly, right, interestingly, you can actually cause electrons to flow through here with zero resistance at absolute zero. Well, theoretically. Some things can do it above that value, and that's where this number comes in. All the atoms may have stopped moving at a higher temperature. This is the lowest possible temperature for atoms which have the least attraction to one another, that they'll stop moving. So helium, right? This is the temperature at which helium stops moving, freezes to nothing, stops moving. Okay. And we'll talk a little bit more about that later. I might be teaching you that slightly wrong, but we'll make sense of it a little bit later. Okay? So anyway, at that point, this stops moving. Now, does this mean this has no internal energy anymore? Does that mean there's no internal energy at this point? So EK of the particles has become zero, right? EK of the atoms has become zero. But internal energy-wise, there's still internal energy because there's still mass there, and there's still some kind of intermolecular or interatomic, if you want, or metallic, if you want, bonding within here. So it's not, internal energy is not gone to zero. What can we say about the heat energy in here now, though? There's how much heat energy, though, in something at absolute zero? How much heat energy? Right. No heat energy. Okay? So there's no heat energy. So heat in this kind of scenario, in this concept, is, in a sense, it's just the kinetic energy of the particles within here. Okay? So I'm trying to illustrate that there's still internal energy, right? There's still, like, if you want, E equals mc squared stuff going on. And there's potentially still energetic relationships between the atoms and the electron clouds around them. But there's no heat because the atoms themselves are no longer jiggling around. Okay? Does that make sense? Perfect. Now let's apply temperature to all of this because we've been mentioning temperature. What does temperature do? What is temperature? Ooh, you know what? That's a tough thing to answer, isn't it? You can say lots of words. Do you really have a good understanding of temperature? I think the best way to understand temperature is to actually think about the tool that we use to measure it to begin with. So let's draw a thermometer, a classic mercury or liquid, if you want, alcohol thermometer. And that is a terrible thermometer, and I'm embarrassed by it. Let's use my shapes here to help me draw a better thermometer. There we go. There we go. Can you help describe the makeup of a thermometer to me? Okay. Okay. Sure. Yeah, we'll use... Yeah, it's a little more rare, at least in high school anyway, to find mercury thermometers. There's like a completely insane fear of mercury. Well, yeah, of course. Yeah, well, mercury thermometers are sort of the standard thermometer, right? So let's say we are a thermometer maker, okay? So what we've got here is we've got a glass tube filled, and it's got a hollow channel down the middle, right? Let's draw that hollow channel. It's a little bit tough to draw, but let's see if I can do it. Yeah, okay. Let's do this. Let's put a hollow channel down the middle. And then there's a globe at one end that contains extra liquid, represented by the little red ball that I drew. Okay. And let's think about what goes on here. So liquid, as we sort of mentioned before, as you heat it up, its particles start to jiggle more, right? As they absorb heat, they jiggle more and they take up more space, and the liquid tends to expand. So let's think about, if we were to manufacture a thermometer, how we might set the graduations on it. And let's do a Celsius thermometer, okay? Okay, so first thing I would do is I would get some water, right? And I would take the water and I would freeze it, and then I'd allow it to come to the point where it starts to melt, okay? And I'm not sure if you've learned this or not, but water will stay at the same temperature the whole time it's melting before it moves up the chain. And what's going on there during melting is these bonds, these intermolecular bonds, are breaking during that time, and all the energy is going into them, and none is going into increasing the kinetic energy. So the temperature stays the same during the bond breaking. So we're increasing the internal energy, but we're not raising the temperature. We're not increasing the heat. We're not increasing the kinetic energy, okay? Does that make sense? Okay. So what we do is we get it to that temperature and we'd see, okay, there's a pause here. All right. And we would say, okay, that's the point we know is 0. In fact, that's how 0 is defined in Celsius, the melting or freezing point of water, okay? Then what we would do is we would continue adding energy in, whether that's with radiation or with heating the air around and allowing it to heat up, or conduction, like putting it over a burning flame and conducting very hot air molecules into it. However we do it, okay, it's going to start to expand. It's going to expand, and then it's going to stop expanding, and we're going to get to the point where now the water is boiling, it's becoming steam, and we define that as 100 degrees Celsius. Okay, so we would start, I should be careful because we would have no graduations on at this point. Okay, we get these 2 points, 0 and 100, and then we would evenly divide them into 100 equal graduations, which we call degrees Celsius. And then we would continue that up and continue that down. Does that make sense? So that's how we would make a thermometer to begin with. Does that make sense? So now the question is, what's going on when we're actually using this tool, right? So this tool that we've now defined based on 2 points within water, okay? We have this Celsius scale. That's not the only way to make a thermometer and define a scale of temperature, but this is now defined as a scale of temperature. It's a Celsius scale, 100 even graduations between 0 and 100. Every thermometer that I build, if I'm building my precision thermometers at the factory, would have to go through this. And I would have to also account probably for the fact that this tube is very hard to manufacture as having a completely uniform cylindrical shape, right? So making thermometers is a little more probably difficult than we might consider if you want to make really accurate ones. Okay, so if I take a thermometer and I put it into a solution, okay, okay, so let's say this is water or something, and we plop this in, okay, how does the thermometer gain, how does it, like, what's going on at this point? I put my thermometer in, and let's say I notice the thermometer rises up to, let's say 45 degrees Celsius. Okay, so it rises to 45 degrees Celsius. Before I put it in, let's say it was at like 18 degrees Celsius. So it went from 18 up to 45 degrees Celsius. So what's happening to make that temperature rise? What must be going on, do you think? What's inside the liquid? Right. Warm particles that are zipping around. Well, at least warmer than the thermometer was, okay? They're actually crashing into the thermometer, and via transfer of momentum, right, they're causing the liquid, well, first the glass, I guess, first the glass that makes up the thermometer to start to jiggle, and then that will eventually transfer the jiggling into this liquid itself that's in here, mercury or alcohol, and then that will start to, transfer the jiggling all through itself, and it will heat up and its temperature will rise, okay? Now, interestingly, in order for the temperature of the thermometer to rise, what has to happen, do you think, to the temperature of the water? It must, because the thermometer is gaining some of the energy that was in the liquid and absorbing it into itself. Okay? So is this water actually 45 degrees before you put the thermometer in? Probably not. It's probably slightly higher. But the thermometer, the act of actually putting the thermometer in, brings both of these to, if you want, an equilibrium. Okay? Interesting. Right. Okay. So if we can like think of that maybe in terms of graphing, it might help. So let's say we have a temp of water. Let's say it's up here. And then we have temp of thermometer. Now, in real life, you know, the negligible difference between the true temp and the temp that this thermometer shows, I mean, it's going to be very small because the thermometer itself has very little mass to heat up, right? It's a small thing, it's light, it's got a tiny bit of liquid in it. It's not going to decrease the water temperature much, but we're going to exaggerate the scenario a little bit. Let's say we have a gigantic thermometer, okay? So this is the true temp of the water. So what's going to happen is the thermometer is going to take some time, and it's going to rise up as it absorbs energy from the water, and the temp of the water is going to decrease as it passes some of its energy into the thermometer. And then they will come to what we call an equilibrium. Okay? So the temp on the thermometer is actually going to be slightly lower than the true temp that it originally was at. Okay? Now, okay, so what we're trying to do now is we're trying to figure out what exactly the temperature is saying about this water. Is the temperature telling us how much energy there is in the water? Is it telling you that? It's not telling you how much energy there is in the water. It is not doing that. It can't tell you how much energy there is in the water. Think about it like this. We're talking about all the energy in the water, okay? But then we say double the amount of water. Well, now all of a sudden we have double the amount of energy, but the temperature hasn't changed, has it? I can have a pool and I can have a bathtub, which are at the same temperature, but one has much more energy within it because it's got more moving particles. It's got more mass. It's got more matter. So it must have more energy overall in it. So what is temperature actually telling us? When we take 45 degrees Celsius, what does that really mean? What is that a measure of? Ah, excellent. That's exactly what it is. It's talking about the speed of the particles. It's really measuring the kinetic energy, if you want, or the average kinetic energy of the particles within the substance. Not how much heat there is, but the average kinetic energy. So temperature, and so what's happening, right, is the liquid within this comes to the same average kinetic energy that the particles within here have, okay? So temperature is just a measure of the average, because they don't all have the same kinetic energy, they have an average, measure of the average. We'll talk about that in a later lesson. Kinetic energy of particles in the substance. And if you're still confused about that, maybe this will help. Okay, let's say we have 2 volumes of water, okay? Let's say this is 1 liter, let's say this is 10 liters, okay? And let's say into this we put, I don't know, let's say we put, better be careful because, well, let's say we put X amount of energy in, so X kilojoules go in, and X kilojoules go in here, okay? We add the same amount of energy into each of these. Which one will have a larger temperature change? The one on the left, right. There's less volume to spread the energy over, okay? So in other words, the kinetic energy, the temp change, will be higher over here. Higher temp change, okay? Temp change will be lower over here. You know this from real life intrinsically. If you were boiling water and you boil a small amount, you put it on the stove to boil, it will reach its boiling point much quicker than a gigantic vat that you're going to boil, spaghetti for 20 people in, okay? You put the same amount of energy in, the temperature change is going to be more in the lower volume. So just before we wrap up, what do we have to consider when we're thinking about how temperature is changing between these two things? Like, what plays a role in that? One thing, obviously, is energy. Energy is going to play a role in what happens with temperature. The amount of energy we put in plays a role, right? But what else has to be considered? Mass. Mass also plays a role. And mass represents how many particles there are there, right? If I have more particles, I need to put more energy in to increase their kinetic energy, right? So we've got energy, mass, and we've got temperature, and there's one more thing to consider. Let's say I take a cast iron frying pan that weighs, like, I don't know, 2 or 3 pounds. Let's say I take an equivalent 2 or 3 pounds of water, and I start heating them both. Which one do you think is going to feel hotter faster? The pan will, okay? Different materials require different amounts of input energy to change their temperature. Water has a high heat capacity because it has hydrogen bonding between its molecules. Whereas something like an iron pan or a steel pan or an aluminum pan, even better, the particles are connected and can transfer heat amongst themselves, A, much more quickly, and B, experience a much larger change in kinetic energy for the same amount of given input energy. So the last thing we need to consider is what's called the specific heat. In other words, how much energy does it take per gram or per mass to change the temperature a certain amount, okay? So these 1, 2, 3, 4 things have to be taken into consideration when we're talking about changes in temperature based on inputting energy into a substance. Does that make it somewhat clear for you guys as to kind of how all this stuff interacts with each other? Because there's oftentimes lots of confusion when we talk about what's the difference between heat, temperature. Why can we have more energy in, say, a lake that's at 4 degrees Celsius than in a bathtub at 75 degrees Celsius? Why can we have that? Well, just think about that, okay? And we'll sign off with that. And one more time.